Hello everyone and welcome to the last day of derivatives. This unit and the rest of this day you're done with technically semester 1 of calculus. So we're going to look at related rates. We'd like you to read this portion first and the problem, and then we'll look at it. Please pause it. So we've got air being pumped into a balloon so that its volume increases at a rate of 100 centimeters cubed per second. So that's the given information. We know that the volume is increasing at 100 centimeters cubed per second. Now that's not important, but we know it's increasing at 100 centimeters cubed per second. That's the rate. Okay? The rate is increasing at 100 centimeters cubed per second. What we don't know is the rate at which the volume, at which the radius is increasing. And the thing that we need to know is that's when the diameter is 50 centimeters. That's extremely important because it increases at different rates. So we want to know exactly when we want to know when the rate at which the radius is increasing. So moving on here, let V, well, that's going to be the volume of the balloon. Let R, well, R is going to be the radius of the balloon. And then as we move on, we know that rate of changes are derivatives. And so if we look here, both the radius and volume are a function of time. We know that it depends on the rate at which the volume and the radius is increasing at that specific moment as a function of time. And these are the rates. And so another way we can look at it is this. So we know that the volume, what we set up there, we know what that is. That's 100. The rate is what we are trying to find. Okay, but what we want to know is the rate when the diameter, or in this case the radius, is 25 centimeters. You don't need the centimeters, I'm just putting it there. And this would be, again, centimeters cubed per second. So we have one given, dV over dt, one rate of change. This is what we're looking for. And so the final thing that we're looking at is the fact that we've now got to solve the problem. We have to look at what we're given. Well, we know the volume of a sphere, which is 4/3 pi r cubed. And this is how the radius and volume are related using this equation. So therefore, if we know dV over dt and we're looking for dr over dt, well, guys, let's just take the derivative and go for it. So dV over dt, that's the derivative of v, equals 4/3 pi is just a constant. So keep it as 4/3 pi. The derivative of r cubed is 3r squared dr over dt again. So we're going to get dV over dt to equal, the 3's cancel out, 4 pi r squared dr dt. Now, I'm going to show you two ways to solve this. So one, we're looking for dr dt when r is 25. So one thing that I can do is divide by 4 pi r squared to get dV over dt multiplied by 1 over 4 pi r squared to equal dr dt. Now the thing that we are trying to find here is the fact that we are looking for dr dt when r equals 25. That's the key. Notice that I did not substitute anything in yet. Please do not substitute anything in. You have to solve for this. Now, when I'm looking for dr dt when r equals 25, I can go back to the given that the volume is increasing at 100 centimeters cubed per second. So I can say this equals dV dt is 100, 1 over 4 pi, and I want it when r equals 25. So now I can substitute in 25 squared here. And this is what dr dt when r equals 25 equals. So dr over dt equals 1 over 25 pi. You can do the math, figure that out. Now, what is this labeled then? Well, it's labeled at, go back up here, centimeters, okay? Centimeters per second. We know what the, we know how it's measured versus what the time units are. And done. So that's one way to do it. The other way to do it, this is our final answer. And then the one thing, before I show you the other thing, this is the rate at which the radius is increasing when the diameter is 50 centimeters. And therefore I want you to write it out as this. The radius of the balloon is increasing at a rate of that when their diameter is 50 centimeters. And leave it like that. And yes, I'm going to be a stickler and ask you to write it out. Now going back to the other way of doing it, which, let's see here, I'll do in a different color, is we could have, instead of right here, we could have, it's not an implied symbol even though it looks like that, we're just going to look over here. And with that being said, poor job on me of writing implied symbols here. Very poor. There is the correct notation. I'm sure some of you are wondering if I was going to notice that. We could have solved immediately here and gone right into the substitution. 100 equals 4 pi 25 squared dr dt when r equals 25. So we could have gone right here, noticed that we could have divided by that 4 pi 25 squared. Now, how do you get the answer here? Well, one thing you can see here is that this could go to 25 and that's gone, and then those, you have two 25s here, that 25 is gone, and that's where we get our 1 over 25 pi equals dr dt when r equals 25. So I solve for dr dt. That's okay to do here. I was just going to show you the shortcut way. I wanted to show you the correct way to solve for dr dt, but then here's the shortcut way that we could have gotten. Notice same answer. I do expect you to write that down here. Okay? Confusing? Read it over. If not, let's go on to the next problem. If I haven't read the question, read it, please. So we've got a ladder leaning against a wall. Ladder leaning against a wall. You're on the ground. On the ground. So this is the ground. Ladder. Wall. The only thing we know right now is that the ladder is 10 feet long. Now, saying here that the bottom of the ladder slides away from the wall at a rate of 1 foot per second. It's asking you, this is the rate. So this is the rate here. Make sure you know it's asking you the rate that this is falling down. Let's hope it never happens to you guys that you're falling on a ladder. It's asking how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall. So the first thing that we have to find out is, what's the equation? You've got to see this whenever you're given a triangle. Go back to algebra. We're going to look at Pythagorean theorem. A squared plus b squared equals c squared. And so we've got to give our own letters to this. I'm just going to call this A, B, and C. This has to be the hypotenuse. It doesn't matter what you say is A and B here. And so, excuse me, what are we given? Let's look at the givens first. We know that C equals 10 feet. And that's really the only thing that's given to us. We're not given that the ladder is 6 feet from the wall. That is not a given. That is actually what we're going to use to find the answer, but it's not a given. And then, so what are we looking for? This is the unknown. The unknown. Not a question right there, but we'll leave it. The unknown is, oh, and the other given, I have it right here, that dB over dt equals 1 foot per second. And we're going to say that it's increasing, so it's a positive 1 foot per second, because it's increasing because it's going out. It's gaining in length. The unknown is dA over dt when B equals, when the bottom of the ladder is 6 feet from the wall. So when B equals 6. And we have our givens, we have our unknown. Now we actually have to go do something with it. We can't find it until we actually have dB over dt, dA over dt. So we're going to take the derivative of a squared plus b squared equals c squared. We're going to get 2a dA over dt plus 2b dB over dt equals 2c dC over dt. Now, where did that come from? I could have put d over dt in front of all of these. To get that, I'm just kind of skipping that step. Now, let's substitute in what we know. The rate at which this ladder changes. This ladder never changes length. This ladder will always say 10 feet. The rate at which the ladder changes length is 0. So that's gone. So that 10 feet really doesn't help us. And we know that we have 2a dA over dt plus 2b, but we know what b is. We know what dB over dt, which is 1, and that equals 0. But you see, we're still at kind of a standstill here because we don't know what a and b are to solve for dA dt. But we have to now use this information that we want to find it when b equals 6. This part is as far as we can go until we need to substitute in what a and b are. So this is actually a true equation that we can solve at any length here for where a and b are. Now we're just going to plug in information. So we kind of go over to the side. So I'll go over to the side here. I need to know what a and b are when b equals 6. So I'm going to have a squared plus b squared equals c squared. I'm going to plug in what I know. I know c is 10, that's the length of the ladder, and I need to know a when b equals 6. So b is 6, and square that, and that's a squared. I need to find that out. Well, it's a squared equals 36 plus here equals 100. And I know a squared equals then 64, and so a equals 8. I know that a equals 8 when b equals 6. So now I go back and I can substitute in what a is. Now I can say I can find dA over dt when b equals 6. That's the reason why I could plug it in, is now I have this given. Plus 2 times 6 times 1 equals 0. And you can solve this. So you can solve it right now. So you will notice that we got negative 3 over 4 feet per second is the rate at which the ladder is falling when the bottom of the ladder is 6 feet from the ground. And I would want that to be written out. Now, notice that I could have found when the ladder was 8 feet from the wall. This rate better be at a faster rate because it's falling. As it falls, it continues to gain speed. So if the ladder is 6 feet from the ground, we know it's negative 3 over 4. If it's 8 feet from the ground, it better be at a faster rate because it's falling faster. That's why we had to find out the information specific to when the ladder was 6 feet from the ground. So this right here can be used for any distance. We substituted and made the notation that this is when it's specifically for 6 feet from the ground. Please know that it's always specific. When you plug that in, you have to notate that. You will, for many problems, have to go to the side and find the specific dimensions for the actual spot that you're looking for the rate. We're going to go to the second video for the last problem.